way of introduction, if you would recall, we've got this energy equation. And it's got a head loss term in it. And so far, what we've got is an equation for what this book refers to as the major head losses. And that equation is what I call the Darcy-Weisbach equation. That needs this friction factor and it's easy to calculate. The friction factor for laminar, for turbulent, the function of two dimensionless numbers. There is an equation that's available to calculate the friction factor. This is the Colebrook formula. As you can, this is something that comes from a bunch of experiments, and it's not easy to get a value for F because it's not an explicit equation for F. That is, F you're trying to calculate is on the right-hand side of the equation as well. So you would have to do this iteratively or have it programmed into your calculator to guess an F and then calculate a new F and go around several times until you settle on a value for, and it's in addition to that, there's these two dimensionless numbers that you need to know, which may or may not be, if this is small, if it's smooth, then it goes away, and if this is large, then this term goes away. So we have sort of bounding cases when it's either hydraulically smooth or fully rough, or it is simpler. But generally what we do is we use the Moody diagram. All right, and that's where we are so far.
So in most cases, when we need to use Moody, you're going to be giving us either the one or the other in terms of Reynolds number or that right?
I think that I could imagine one where you're just given the two numbers, given the relative roughness and the Reynolds number. Look up that. Yeah? Or you could be, it's a cast iron pipe
Yeah, no.
of 6 inches and the velocity is such and such, where you'd have to do some calculations to get the two numbers and then come up on the movie diagram. Okay, so, but even if you can do that, it turns out that, and you come up with the friction factor, that there's more than just those sorts of head losses that we have to worry about. There's another part of this, minor losses. For the major losses, it's likewise a function of some dimensionless number. Both of these are dimensionless that you multiply times your velocity head. But for the minor losses, we have these minor loss coefficients. What sort of things can give you these sorts of minor losses? Okay, so these, they fall into these categories, and for any particular example, you could have one or more of one particular type of minor loss causing part. Just as an example, qualitatively, here's an example where you might be given, well, it could be any one of the types of problems. Any one of these three types of problems could include minor losses in the calculation. And so for this problem, we wrote out the energy equation and had that head loss term, we could have and each of the other, or the minor losses, could also contribute to the head loss. That is the and I like to think of just a modification to the energy equation that we can make to include the minor losses. Instead of just having the friction losses, you add another dimensionless number that accounts for all the minor losses, and you multiply that times the velocity head. So it's sort of a modified Darcy-Weisbach equation that has both height friction and minor losses added to it. And I got this just to say that there might be several separate loss coefficients that you'd have to consider in solving a problem. All right, so working these sorts of problems is pretty much a table lookup for each of the terms that contributes a minor loss. And I'll go through them just to give you a sense of the ranges of values that you might expect and what it depends upon. But to solve these problems, you'll actually go to a table, a figure, and pull out a case of L for that particular part. All right, so entrances. So I think, in trying to remember which thing is an entrance and which thing is an exit, I think of, have the mind, keep in mind what's happening to the water with respect to the pipe. It's an entrance to the pipe and it's an exit from the pipe. That's what this entrance refers to. So imagine we have a reservoir back here and the water is entering the pipe. This is called a re-entrant entrance. And it has a pretty high case of L relative to one that's smooth, where you don't get these eddies, the recirculating water that the kinetic energy here of this water swirling around eventually gets transferred as to heat. And so that flow energy, you're losing some in generating these eddies. You don't have something like that in a well-rounded and you can get a low close to zero case of L. In between is the simplest one that's just square edged entrance. And there's a table of values with figures associated with them to give you more possibilities. So the K's can be sort of low, medium, and high. Yeah, well,
For all of these diagrams and all of these tables, especially for like something like Moody, these are all going to be on the next exam, right?
they will, yeah. You're not, yeah. Anything you would need in the way of reference material that's available, I'll give to you.
Okay.
Moody diagram, yeah.
And do you know, for the homeworks, are we gonna need to know these values, or?
I think generally, this would only be in homework 7, and I don't recall if there's a problem that includes minor losses. I believe there is.
Okay,
Uh,
I'm sure the book has it then.
Yeah, but they're in the text, yeah, and I don't have the table reference, but I do for some of these other parts here. Going on to exits. For an exit, the shape doesn't matter. There's no real advantage to rounding the corners because it's going to lose all the velocity energy it has. The shape doesn't matter. So that's the easy one. Just know that the exit case of L is 1.0. Yes, I do have the out of the text, there are table and a figure. It depends, they do this stylized R to give as a function of the radius of a bend, and 45, 90, 180 angle, smooth to rough pipe, small diameter to large diameter pipe, small diameter, or small radius to large radius bend. And they, depending on what you come up with for all of those factors, you'll get a case of L that's down a 0.1 range for smooth pipes and large radius bends and low angles, all the way up to tight radius, rough pipes in small diameters. Yeah. So, and you would go to those tables to look it up. These are a little tricky, contractions and expansions. Because as you're quantifying the velocity head, you've got two possible velocities. And so, but the figures, there is a figure, they are clearly marked as to whether that case of L gets multiplied times the velocity head V1 or the velocity head V2. And you can think of these like contractions kind of like an entrance and expansions kind of like an exit. So for contractions, the shape of it matters, whether it's abrupt or smoothly varying. It doesn't so much matter on the expansion shape, what its shape is, but what does matter is the that there's an area ratio that you can calculate from A1 to A2. And there is an equation for the case of L that's a function of that. And, I'll have to admit that I believe there's a squared on this. I would double check. I wrote that, it's in my notes, and then I looked at it, and I'm not sure that whether the square goes here or if it goes there. But there's an equation in the textbook for that case of L. And I can't figure it out from, this will go from 0 to 1. Yeah. So this thing will go from 0 to 1. All right, and so then we're on to the last one. There's not much you can say categorically about valves, because an open valve of a good design can have a small case of valve and that very same valve, when it's closed, can have a case of valve that's very large, that is much greater than 1, to the point that your Q is 0. So there was a question on that first question on the test. It said there's a flow restrictor that limits the flow to a particular value. You might do that by having a valve that's open to varying amounts. Then the head loss from that valve changes, and therefore the flow changes.
The equation's right.
Okay, that's right. Thank you. All right, so Schwing confirms that this is the correct equation.
Ariana did too. I just
Oh,
want to throw it
Ariana,
out there.
thank you, Ariana, for checking that for me. All right, and so there are some figures to go with this. All right, so we don't have time to go through a full problem, but I just wanted to show the sort of problem you might come across. Let's look specifically at that problem we had previously. Imagine that the water surface elevations of 2 reservoirs varies by 100 meters. There's 5 kilometers of pipe, and so we're given all these things. Okay, so and you might be asked to find with this information, you've got to find the case of L's and then find the pipe size. So how do you solve this problem? Well, this is our three types of problems. This is the type 3 problem. This is a design problem. And where we would start is figuring out what the K sub L's are. Go to the various tables and look up the values. So there are your,
How would you know the KL of the elbows if you don't have the area?
well, you know, I said that I found one of the tables saying that if it's a 90-degree flange, and I didn't look to see if there's a limit on the pipe sizes, but I pulled this out of one of the tables in the chapter. Yeah, I had previously said it was more complicated than that, just saying that it's, you know, only these two things. We don't know how smooth the pipe is, but I did find that information. Okay, so we've got that, and so that the sum of our K sub L's is this. We go to our usual set of equations. This is where we'll end it, to say that from the energy equation, we've got that from our energy equation. We've got continuity, steady state continuity, the relationship between flow and area. And we can get friction factors from Moody diagrams. So we've got three separate pieces of information that we use to I believe, you know, Nathan, you were asking if there is a minor loss problem that's a discharge problem, a slightly easier version of this. But I do think that there's either a type 2 or a type 3 problem on the homework that uses minor losses. This is a type 3 problem where, just like we had done previously, in solving that problem, you'd guess an F of 0.03 and then use this to get the V, or you'd actually do a different version of this equation that has Q instead of V, and then get the flow, and then from there get the Reynolds number, the relative roughness, get an updated F, and go around again if you need to solve for the diameter. Yeah, use this to get your diameter, right, given the known flow, because your flow is given And once you get a diameter, get a Reynolds number and a relative roughness, and update the friction factor. That's where we'll leave it. Are there questions I can answer? Anybody?
There was one, I hope I answered it right, but was the length the total length of the pipe, or was it just the distance between?
Oh, it
The
would be
two.
the total length of the pipe.
Okay.
Yeah.
Yep.
Yeah.
So, for these kinds of problems, or not for these kinds of problems, for the homework 6, we will be doing in class, like in person, like we've done the last couple homeworks this Friday, right?
This, yes.
Okay.
Yes. That's my plan.
And I said that probably.
That's my plan, and we're gonna do it, I am gonna do it here, confirming, assuming I have to go out of town for a, doctor's appointment, assuming that all goes well, they let me out in time, I should be back here.
Okay. And that'll be, well, no, never mind.
That'll be the 12/20
Yeah,
on
we
Friday.
talked about, but I was gonna say, the thing next week, the test prep thing is gonna be at 5:30?
I think it's all on the calendar, I believe it's 5:30 on Tuesday,
Okay.
but, that's my recollection, I would consult the calendar.